Spider-Man, Spider-Man, does whatever a spider can. So Spider-Man was swinging on his web and the web snapped. Which direction would he travel? So here he's traveling around a circular path as he's swinging. If we think about a circle, it's really a whole bunch of small little straight lines. You can kind of see that on that dashed line there. So at this point, if his rope were to snap, he would go off in that direction. Or here, if the rope were snap, he would go off in that direction. Maybe you've swung something around in a circle over your head sometimes, and you've seen how terribly wrong this can go if you let go at different points. So Spider-Man is swinging around, and his velocity looks like this. We would say that's tangent. So his velocity is tangent to the circle at all of these different points. Now, Newton's first law says an object will keep doing what it's doing until another force acts on it. So Spider-Man isn't doing what he was doing before. He does not go flying away unless his webbing breaks. So this means that there must be something changing Spider-Man's velocity. And we have a name for a change in velocity. That is acceleration. So there is an acceleration acting on Spider-Man. So Spider-Man has a velocity in this direction. If we think about the direction the velocity is changing, so the velocity is turning this way, we need an acceleration that's going to be turning the velocity that way as well. The only thing that Spider-Man is in contact with is that webbing. That's the only way that he can accelerate. So Spider-Man's acceleration is actually towards the center. We call this centripetal acceleration, and we are going to spend this week, quite a bit of time this week, talking about centripetal acceleration, centripetal forces, and what it means. So centripetal force is a center-seeking force. This force is always perpendicular to the object's velocity vector. So if I have an object here and it's traveling with a velocity that's tangent, so there's the tangential velocity, that's the velocity of the object traveling in a circle. The centripetal force is always going to be perpendicular to that towards the center. So the centripetal force is a center-seeking force. Now, if I want to identify the acceleration, well, the acceleration is the same direction as the force. Remember, force is just mass times acceleration. So the only difference between acceleration and force is multiplying the acceleration by the mass. Okay, so here I have a cup of water. There's water in there. I'm going to put it on this thing. And using the power of centripetal force and inertia, I'm going to spin it and not get wet. Isn't that impressive? Yeah. Now, what we feel is something maybe a little bit different. So if you think about what's going on when you're traveling in a circle, so we have our centripetal force, our tangential velocity. If you've ever been in a vehicle that's been going relatively fast around a curve, do you go towards the center? I don't think you do. I think what you feel is a force that's actually acting outwards. Now we have a name for that as well, and that's the centrifugal force, although I'm going to put this F here because that is a fictitious force, meaning that it does not exist. However, it feels very real. If you've been in a car and you're going around a circle, I've played this game lots, and you're slamming someone up against the car door, it feels like there's a force acting outwards. When in fact, centripetal forces are acting inwards into the center of the curve. Now the reason why you go flying outwards is because of Newton's first law again, which is the law of inertia. So if you think about your velocity is in this direction. You want to keep traveling in that direction until something tells you not to. And that thing is usually the car or the seatbelt or the door. So the reason why you feel a centrifugal force is because of inertia. So that's your inertia and your tendency to keep on doing what it's doing. So with great physics concepts come great physics equations. I didn't say that, Spider-Man did. But we have some equations here. We're first going to look at where these equations for acceleration come from, and velocity, and then we're going to look at these equations for forces. They're all in your data booklet. Now to find the tangential velocity, okay, if you think about it, we're traveling in a circle. Velocity is just distance over time. The distance around a circle is 2 pi r. And the time to complete one revolution we call the period. So the tangential velocity in meters per second is 2 pi r divided by the period. Sometimes we're given frequency, so remember period is 1 over f, but 2 pi r over t is how we would calculate the tangential velocity. Now if you think about 2 pi r over t, here we have Spider-Man. Spider-Man is 11.43 centimeters from the center. The Hulk is half of 45.72. If we think about who's going to be moving the fastest, so v is equal to 2 pi r over t. As the radius goes up, so as Hulk gets further away, as the radius goes up, the speed needs to go up. So Hulk is going to have a greater tangential velocity than Spider-Man. And if you were to spin this, you would see that Hulk would go flying off. Spider-Man would stay on a little bit longer. As they spin, their velocity is constantly changing, but they can't be moving constantly at the same velocity. So who would have the greater acceleration is the question. If we think about Hulk again, Hulk has a greater velocity. So if there's a greater velocity, then there needs to be a greater change in velocity. I have more velocity to change. So I think Hulk would have a greater acceleration compared to Spidey. Now there is a formula for centripetal acceleration, which is v squared over r. So we have two similar triangles here. And it's really trying to take, okay, so we have our change in velocity. So our change in velocity over our time is our acceleration. And from these triangles, we end up with acceleration as v squared over r. So a is the centripetal acceleration, v is the velocity squared, and r is the radius in meters. That's one equation. If we take both those equations that we had, so we take the acceleration and the velocity is 2 pi r over t. So we can take this, again, this is 2 pi r, this is v squared, 2 pi r over t squared. So I take my centripetal acceleration is 2 pi r over t, and that's squared divided by r. That's that first equation. I end up with this equation that also works for the acceleration. Now this one requires some different quantities. So if I have the period or frequency, I can get the centripetal acceleration is 4 pi squared r over t squared. So those are two formulas we have for centripetal acceleration. So acceleration is v squared over r, or acceleration is 4 pi squared r over t squared. Those are ways to calculate that center-seeking acceleration for things moving in a circle. Going a step further, we can get our formulas for forces. Remember, force is just mass times acceleration, so we have centripetal acceleration formulas. All we need to do is multiply those by the mass, and I will have an equation for a force. So the centripetal force formula is mv squared over r, or m 4 pi squared r over t squared. All we've done is multiplied it by mass, just like we've done with finding force in all these other ones. Again, that's Newton's second law.
Oh my
So that
God.
was a crazy video. And again, when we talk about who has to try harder to hold on, gets back to Spider-Man and the Hulk. If you're on the outside, you have a larger tangential velocity than if you're on the inside. So there is you have greater inertia, and so you have to try a lot harder to hold on. Also, you need to match that centripetal force. So here we have a 32 kilogram child sits on a rotating merry-go-round 2.5 meters from its center. We want to find the centripetal force. So Fc is equals to mv squared over r. So the mass of the child is 32 kilograms times v squared, so 2.9 squared divided by r, which is 2.5. So that's 108 newtons. And then the question is, if the child does not move, what is the force of friction acting on the child? So this child is traveling in a circle. We have the centripetal force acting in. If this child is not moving, then that force of friction needs to be holding that child in place around the edge of that. So my centripetal force is the force of friction if that child is not able to move side to side either way. So my centripetal force is 108 newtons. My force of friction is 108 newtons as well. So going a bit further, we're going to look at building some equations, calculating the net force, what's actually going on, what is contributing to the centripetal force. So if an object has the same velocity but is just changing direction, then an object must also have the same magnitude for acceleration. If the acceleration does not change, then the force does not change either. If you think about like a bucket traveling in a circle, if we have it moving at the same velocity, it has the same acceleration, the same centripetal force. However, at different points, that can be due to different sources. So for example, here we have an object traveling in a vertical circle. I guess we need a string acting on it, so it travels in a circle. So if we hold a yo-yo and we were to spin it around, at these different points we have different forces. So at the top here, I have some forces acting down on it. I have tension, and I also have the force of gravity. At the bottom, all the forces that are kind of important, I have the force of gravity, and then I have tension that actually has to be greater than it was at the top because now it needs to counteract gravity. And then when I'm at the sides, I just have tension because gravity is going the other direction. So if we think about the centripetal force, it's the center-seeking point force at all these different points, but at the top here, it's tension plus gravity. At the sides, my centripetal force is just tension. And at the bottom, my centripetal force is tension minus the force of gravity. So by drawing free body diagrams, we can determine, okay, what is that centripetal force and what are the forces that are actually contributing to it? Here we have an object traveling in a horizontal circle. So here we have a car, we have the centripetal force here. It doesn't go flying off the road. So the centripetal force needs to be equal to the force of friction for this car to travel around in that circle. If I think about an object in a loop, well, now we're talking about the normal force. So maybe at the top of the loop and the bottom of the loop, at the bottom of the loop here, so my centripetal force, I have the force of gravity down, and then I have the normal force pushing back. So my centripetal force at the bottom of that loop is the normal force minus the force of gravity. And at the top, if I'm on the inside of the loop, here I have the force of gravity and I have the normal force. So my centripetal force at the top is the normal force plus the force of gravity. So it really depends on the situation. We need a good free body diagram. The centripetal force is really what forces are contributing to that center-seeking force, that centripetal acceleration. So here's a question. Why are indoor cycling tracks sloped? So if we think about going around in a circle here, so if I were to just drive around in this circle, so how fast can a bike go before it goes off the edge? So we have the centripetal force is equal to the force of friction. If the centripetal force is greater than the force of friction, then it all falls apart. So I have mv squared over r is equal to the normal force, which if we're going straight up and down is mg. So mu times the normal force is my force of friction. And get rid of my m's. So I get v is the square root of mu times g times r. So I'll put that on my calculator. So square root of mu, which is 0.8 times 9.81 times a radius of 20. So that's 12.5 meters per second, which is only like 45 kilometers an hour, which if you think about Olympic cycling, it's way faster than that.
Let's see what he does then. Sam Litley into his stride. It's just a straight ride of 1 kilometer to see who takes the world title. It's a
So why are the tracks sloped then? If you think about that centripetal force, so the centripetal force, we want to increase it now without kind of losing out to friction. So if it's just a flat track, we're going to fly off and eventually we overcome friction. However, if the track is sloped, there is a component that I push against the sloped track, and that normal force actually helps me move in a circle. So just on a flat track, there is no help from the normal force. I'm really just relying on friction to keep me there. When I have a slope track, I have the normal force, and I also have the force of friction, which is helping push me towards the center and make that curve at very high speeds. That's why some racetracks have slope tracks as well, to help you make those curves at very, very high speeds.